Okay, I will start now. Uh, okay, this is a MOSFET structure. Okay, as I have told already, the different okay parts. Okay, this is body or bulk or wafer. Okay, this one is wafer or body, or we can call it as a bulk. Okay, this whole thing is called body or bulk. Okay, this is lightly doped, and okay, this is heavily doped diffusions. Okay, here you are taking P type substrate, means P type semiconductor material, and diffusing with the heavily doped N plus semiconductor material here and here. Okay, here for isolation, okay, here we will use fixed oxide. Okay, thick oxide. This one thick oxide for isolation for the beside devices. Okay, here one transistor. Okay, here one transistor and beside other transistor. So to isolate from each other, we are depositing the fixed oxide or thick oxide. This one, and here this is gate oxide, then polysilicon gate terminal. Okay, here NMOS device, N-type source and drain, and P-type body connected to ground. Okay, as it's already told, NMOS, this body is connected to source or always connected to ground in the NMOS. But whereas in the PMOS, okay, this body always connected to higher power supply or VDD. Okay, this body for PMOS always will connect to VDD higher power supply, and in the NMOS this body connected to ground. Okay, this CMOS technology you will see later. Now we will concentrate only on NMOS and PMOS transistors. Okay, the symbols already we have seen. Okay, this is the okay MOSFET operation. MOSFET operation. So this here N MOSFET, your body is okay P type substrate, P type substrate on. This is bulk and N plus diffusions, N plus diffusion. Source and drain, N plus diffusions, and here gate terminal. Okay, this is silicon dioxide. Okay, insulation layer. Okay, the P type substrate. Here electrons are the majority charge carriers, and these electrons are the minority charge carriers. Okay, here diffusions. The source and drain are heavily doped diffusions. Okay, here gate is polysilicon. Okay, for gate terminal we will always use polysilicon. And okay, here the MOSFET operation. Okay, there are three types of operations. Okay, First one is okay cutoff region of operation. Next triode or linear region. Next one is saturation. క్లారిటీ లేదా? Here when okay we will apply gate to source voltage. Okay, we will use gate to source voltage. Here VGS gate to source voltage. When this VGS less than VT threshold voltage means uh, when this condition okay this device is off condition, there is no current flow in the transistor. Okay, when we apply this VGS less than VT, okay, in the P type substrate, okay, here holes are the majority charge carriers and electrons are the majority, electrons are minority, holes are majority. Okay, when we apply positive gate voltage, okay, here positive gate voltage and so here positive gate, okay, when you apply here positive gate voltage, okay, here when we apply positive gate voltage here, okay, uh, okay, when we apply here positive gate voltage, here positive holes at here, this oxide, and here majority carriers are here holes. Okay, when we apply positive gate voltage, this here positive charge and the P types substrate also positive charge. Okay, because of this same charge, this positive okay carriers they refill each other and okay they will attract toward your negative terminal. Okay, this bulk is connected to ground, your source. Okay, this positive charge carriers attracted toward the ground, and here positive charge, because of positive charge this negative electrons attracted here near this okay insulation layer. Okay, this near this insulation layer, these okay negative electrons are attracted toward this insulation layer. Okay, when we keep on applying the positive voltage more, okay, there is a inversion layer here across the this insulation oxide layer. Okay, when this VGS some greater than some voltage, okay, this insulation layer uh, okay because of this extra gate to source voltage, this insulation layer, this VGS can overcome this insulation layer and electron flow from your source to drain. Are you following? Okay, because of this higher gate to source voltage, uh, initially when the smaller VGS gate to source voltages, uh, this negative charges across the insulation layer and here positive charges across gate. Okay, they will form. They accumulated at the insulation layer. When we keep on increasing gate to source voltage, this VGS can overcome this junction, this insulation junction, and at particular voltage, these electrons at the junction, okay, they can flow from source to drain. Okay, that voltage is called threshold voltage. Okay, here what is threshold voltage? Okay, threshold voltage is the voltage at which the electron flow from, okay, source to drain. Here, source to drain. Okay, and at particular some voltages, these electrons and holes recombine each other. Here, recombine each other at more the VGS voltage. Okay, after recombination, these electrons at the insulation layer, okay, they can flow from source to drain. Thus, this gate to source voltage can overcome this oxide, SiO2 layer oxide, and channel is formed. Okay, initially, there is these negative charges accumulated at the junction, but particular gate to source voltage, okay, that junction, this VGS can overcome, and their channel will be formed here, and electrons can easily flow from source to drain. Okay, then we will get drain current here. When this VGS less than VT, okay, there is no current, ID is 0. Okay, that is called cutoff or accumulation. Okay, this is also called inversion because of these both charges at the junction, okay, there is no current. Okay, that is okay, this region is called inversion layer. When VGS greater than VT, this inversion layer disappear and channel is formed. Here, if you see here, when VGS greater than VT threshold voltage, and here when VDS also, when VDS is 0, VDS means this one. Okay, this one. This is called VDS, drain to source voltage. Here this is gate to source voltage. Gate to source voltage. VGS less than VT and VDS is 0. Okay, no current. That is cut off. And VGS less than VT. Okay, across this terminals, drain, source, drain, here gate. Okay, there is a depletion layer formed at the interface between the this N plus diffusion and this P substrate. Okay, in the depletion region, okay, there is no charge carriers present. Okay, only here at the junction. Okay, because of these two opposite charge carriers, okay, there is a these carriers will present here. When VGS greater than VT, okay, then this electron will start from source to drain. Here triode region. Okay, triode region or linear region. Okay, when this one, when VGS gate to source voltage greater than or equal to threshold voltage. Okay, here VGS greater than or equal to threshold voltage, then VDS less than VGS minus VT, means here drain to source voltage. This drain to source voltage less than VGS minus VT. Okay, here also there is current flow. Okay, this region we call it as a triode region. This region we call it as a triode region. Okay, here electron flow, here source to drain electron flow, and current will flow from drain to source like this. Electron will flow from source to drain like this, and current will flow from drain to source. Here channel is N type. Okay, here this is P type substrate. Here both are N plus diffusions. So here channel also N type channel. Okay, when we keep on increasing this gate voltage, okay, there more number of electrons flow from source to drain, and okay, there is a current at the drain. Here threshold voltage VT is the potential difference between gate and source. VGS just enough to invert the channel and let the current flow. Means uh, this gate to source voltage is the required voltage to cross this inversion layer. This cross this inversion layer to overcome that inversion layer to start the current flow. Okay, that is called the threshold voltage VT. Okay, in triode region the current is okay, current equation is okay, it is also called linear mode of operation, and current flow increases by increasing both VGS and VDS. So when we keep on increasing this gate voltage VGS and VDS, your current increases linearly. Okay, in the graph you will see, okay, current increases linearly. At in the saturation, current will be constant. Okay, here current equation is okay, I is directly proportional to VGS minus VT into VDS minus VDS square by 2. Okay, okay, this equation is for the okay triode region. The linear mode of operation, the current equation is this one. Okay, now we will see saturation mode. Here VGS greater than threshold voltage, and here VDS equal to VGS minus VT. Okay, here two equations. VGS greater than VT. When VGS greater than VT, okay, already channel is formed here. Already channel is formed, and VDS equal to VGS minus VT. VGS minus VT. Okay, yet for two voltages, gate to source voltage and drain to source voltage. Okay, when we apply these two voltages at the gate and at the drain, okay, here channel is formed, but here at particular condition, okay, when we apply these both voltages, okay, here VDS, okay, because of this gate to drain to source voltages here channel will be narrowed. Your channel will be narrowed here. Your channel will be narrowed because of this drain to source voltage. Okay, because of that only small amount of current flow, and here when this VDS greater than VGS minus VT, okay, here channel will be pinched off. Okay, channel will be pinched off means okay, whenever VGS greater than VT, VDS greater than VGS minus VT, here current flow is constant. Okay, almost independent of here drain to source voltage. This one VDS. Okay, here channel is okay disappearing means pinched off. Yeah, channel is pinched off means okay because of this drain to higher drain to source voltages, when VDS increases, okay, when VDS increases, okay, across the drain terminal the channel is narrowed. Okay, the channel is narrowed. Okay, that condition is called pinched off. Okay, here at the pinch off condition, your current is constant, almost independent of drain to source voltage. That we will see. Okay, threshold voltage. Okay, these are the threshold voltage factors which are included for the threshold voltage. Okay, this threshold voltage depends on the depletion region and the inversion region and gate oxide thickness. Okay, these are all the factors. Okay, is not required, and this is also about threshold voltage. Okay, if you see your graph, okay, here MOS transistor current and voltage characteristics or IV relation. Okay, here x-axis is drain to source voltage, y is drain current ID. Okay, this is the triode region or linear region. Okay, this condition is whenever VGS greater than VT and VDS equal to VGS minus VT. This condition, this is linear or triode region. Okay, here current increases here somewhat linearly, and here in this saturation, here also two conditions, whenever VGS greater than VT and VDS greater than VGS minus VT. Okay, here channel is pinch off and you will get constant drain currents. Okay, you will get constant drain currents. Okay, this is called the saturation region. Okay, this region is called saturation region, and here current is constant for particular gate to source voltages. Okay, this region is called okay we call this region of the device acting as a constant current source. Okay, at this region we call the transistor okay acting as a constant current source, because your current is constant. See, your current is constant, here also constant at particular gate to source voltages VGS. Okay, VGS 1 volt, VGS 2, 3, Okay, we did in the lab. Okay, here id as a function of vds, and here, okay, square root id as a function of vgs. Okay, here this is also called transfer characteristics. Okay, transfer characteristics of mass. Here vgs versus id. Okay, here vt, this is called threshold voltage. Okay, at particular voltage we will get current, and that current increases linearly. Okay, that current is called, okay, at that voltage we call it as a threshold voltage. Okay, at particular drain to source voltages. Next, channel length modulation refers to the fact that due to the enlargement of depletion layer on the drain side, and hence reduction of channel length id is slightly increases as vdd increases in saturation. Okay, uh, because of this drain to source voltage. Okay, when we increase drain to source voltage, okay, when we increase this drain to source voltage, okay, there is a reduction in the channel length at the drain side. Okay, because of that there is no, okay, increase in the current. Okay, current will get constant. Okay, that is called channel length modulation. Here this MOSFET model. Okay, this is the just, okay, 2D structure of the MOSFET here. Here source, drain, gate. Okay, this is body or bulk. Okay, this is channel length, and this is channel width. Okay, this is a small signal model, gate, source, and drain. Okay, this is small signal model. Okay, here it operates three modes: saturation, here condition. Okay, VDS greater than VGS minus VT. Okay, and here linear VDS less than VGS minus VT. Okay, for these three conditions, okay, current equation id equal to k and s w by l into vgs minus vt whole square plus 1 plus lambda vds. Okay, when we include this channel length modulation, okay, this lambda will come to the, we will include in this equation. In the linear, okay, the id current is this one. Okay, here k and s is uh, the factor, includes the oxide thickness and okay, their material properties. Okay, w is the width, l is the length. Kn is the mu1 cox. Okay, mu1 is the electron mobility, cox is the oxide capacitance. Okay, now here mass capacitance. This mass transistors offer some capacitance here. CGS is the gate to source capacitance. CGD is the gate to drain. CGB gate to bulk. CDB drain to bulk. SB source to bulk capacitance. Okay. At high frequencies, these parameters also we will include. Okay, high power applications we will uh, consider these parameters. Uh, Average gate related capacitances. Okay, cutoff triode saturation region not required. Uh, okay, okay. See, first one is NMOS enhancement mode transistor. Okay, NMOS enhancement mode transistor. Here P is the substrate and gate source. Okay, here source, drain, gate. Here substrate. Okay, this is N diffusion and this one is called oxide. Okay, here notations we can see here for here source, gate and drain. Material you can see here. This is metal. Okay, here vertical, just vertical symbol. Here vertical symbol is there, metal. And for gate below this metal, okay, we will use polysilicon. So okay, some problem here. See substrate. Okay, just indicating. Okay, this symbol. Okay, substrate. We are indicating this symbol, and here N diffusion. Okay, indicating. Okay, vertically like this. You can see here N diffusion symbol is like this. Okay, here also same like this. We are representing N diffusion. Okay, this way. And here N diffusion here. Okay, uh, next polysilicon. Okay, like this, representing polysilicon like this. Here you can see oxide. Okay, here oxide is representing like this. Okay, depletion layer just empty. You can see here depletion layer, here also depletion region, indicating like this. P type substrate here just representing like this. Okay, we'll use for the remaining transistors. This is for the NMOS and for PMOS. Okay, remaining all same. For N and P diffusions are different. Here N and P diffusions are okay. N diffusion is very small, very small. Gap is very small. For P diffusion, this gap is very large. compared to N diffusion. అయిపోయింది. స్టార్ట్ చేస్తా, ఆఫ్ చేస్తా.